Welcome class to our video notes on section 2.1 part 2, where we will be comparing the graph of a function with the graph of its derivative. So some quick vocab review is tangent line. We talked about this in our last video. It's a line that touches a curve at one point without actually crossing through it. So looking at this picture here, we see this line is tangent to this curve at the point P, because the tangent line is sort of mimicking what the direction of that curve is doing at that point. And this line is showing us the rate of change of the function at that point. Here's another picture here where we see one that is a point of tangency and one that is not, right? Where the line crosses through it is not tangent. Tangent is where the line is sort of laying alongside the function. They intersect at just the one point. So it touches at that one point but does not actually cross through it. So why is that such a big deal? Well, it has to do with what a derivative is. Okay, so we know that the derivative of a function at x, or we talked about this in the last video, it's the instantaneous rate of change of that function. It's showing us the amount at which the function is changing with respect to x at any given x. So what is that? Like, how do you find an instantaneous rate of change? Well, it's the slope of the tangent line. Not the slope of the secant line, the slope of the tangent line. The slope of the line that's just touching the curve at a point versus crossing through the curve. So here in this sort of image here, you can see that we have a point that's sort of traveling along the curve. And then we have the line tangent to the curve at that point. And you can see that for each different point, there is a different slope to the tangent line. Well, that slope of that tangent line at each different point is the derivative of the curve. It's the instantaneous rate of change of the curve with respect to x. So if you were to put a collection, like if I were to take a collection of all these different slopes at all these different tangent lines at all these different x values, and I were to gather it all together, all the different ones, well, that would give me the derivative as a function of x. Let me illustrate to you a little more what I mean. Take, for example, this graph I have here. Okay, so on this graph here, I have designated this point B to be a point that just travels along the curve. So as I click and drag this point, it never leaves the function. So it's a point on the function. And then I also have a tangent line to the curve at that point. And just like we saw in our last illustration, this tangent line, the slope of it is changing as I move the point around, because at each different point on the graph, the tangent line has a different slope. And that slope is showing us the instantaneous rate of change of that tangent line. It's showing us the derivative of the curve. So let's just kind of highlight what the different slopes are. Down here, where x was more negative, look how steep those tangent lines are and how largely positive the slopes are. But as my point moves closer to the top of this graph, you can see the tangent itself gets less steep, and look how much less the slope is. It's still positive, but it's significantly smaller value because this line, the slope, is a lot flatter because the function is not moving as quickly. The rate of change up here is not as fast as it was over here. And then as I get to the top of that curve, we can see that the slope, the line flattens out completely, and the slope basically wants to go to 0. And the slope values are really tiny decimals, and they actually are 0 right when I get to the top there, which I'm having a hard time making this do. And then on the other side, now the slopes are negative because the tangent lines are facing down. So suppose I created another point. It's down here. Now, what is the significance of this point A? Let me show you. Let me move my B around here. Okay, look what A is doing. The value, or how I'm getting the coordinates for point A, maybe I'll go right here, right there. This point here consists of, first of all, it has the same x value as the point B on the curve. So the x's are the same. The y coordinate of this point is equal to the slope of the tangent line to the function at this point. So that at this x value that they share, at that different x, this slope of negative 0.34 is now the y coordinate of this point. So this point has the same x coordinate as the graph of f, but the y coordinate is negative 0.34 because it's the slope of the line tangent to the original function. So x coordinate is the same, y coordinate matches the slope, okay? So then as my slopes go into the positives, you can see, well actually right here when the slope was 0, or close to 0, the point on my derivative would be on the x-axis. As my slopes go over here onto the side where they were positive, you can see this point now has positive y coordinate. So again, the y coordinate of this point that I created is the slope of the line tangent to the original function. So what if I could see all the collection of all the different slopes of all the different tangent lines at all the different values of x along this curve. Let me try to fill it in right there. Let me come over on this side. Get all these points over here. Nice and solid there. What are you noticing? I hope you're noticing that this is not some random graph with like just random dots everywhere. This is another function. Like this is its own function. And where did I get all these points for? For this new graph here, they were the slopes of the tangent lines to the original function. Those slopes became the y coordinates on this new graph that I just created. This new graph that I just created is the derivative of my original function, my original purple function over here, which was this x cubed graph. It's a cubic function. I was able to form the derivative of this function graphically by taking the slopes at each of the different tangent lines. These numbers you see over here, 1.82, 2 point whatever, 3 point whatever, and change them and turn them into y coordinates on the graph of my derivative, and it creates the derivative as a function of x. It's its own function. This is like, you guys could probably tell me an equation for this. In fact, extra credit to those of you that can figure out what the equation of this derivative is. Now we could find it using the limit process, right? We learned how to do that. Some of you may know the derivative rules already, but this definitely looks like a quadratic function. This is a graph of a parabola for sure. So you could probably come up with the equation for this derivative, but notice that graphically, all it is just a collection of all the different points where the y values were the slopes of the tangent lines to f. So to recap, the slopes of the original function, or the slopes of the tangent lines to the original function. By the way, that's the same thing. Slopes of the tangent lines to the original function is basically just slopes of the original function. All those different little slopes of all those different little tangent lines all along the curve, that's slopes of the original function correspond to the y values of the derivative. Okay, so graphically, what does that mean? Well, here's an example, because when we start graphing these by hand, we're going to be looking for some obvious slopes. We're not going to be able to find slopes that are like 0.379 or whatever. We're going to look for some like real obvious slopes when we're trying to sketch this out. So this picture kind of shows you, find the zeros. Find the zero slopes and start there. Look at this. I have a quadratic equation here that changed direction right here. Well, if you were to draw a tangent line there, it would be horizontal, which means its slope would be 0. So on the graph of the derivative, that's a y value of 0. The slopes of the original function correspond to the y values of the graph of the derivative. Horizontal tangent lines, because horizontal lines have 0 slopes, those correspond to zeros on the derivative. And you can see this in this example here, right? I see boom, boom, 2 zeros, 2 spots where there was like max or min. That kind of was like the example we just did, right? These cubic functions have 2 places with 2 horizontal tangents. Their derivative is going to have 2 zeros, just like a quadratic, right? These quartic ones, they've got these 3 different places where they're changing direction. So that's 3 different zeros on the derivative. Derivative's going to be cubic. This is all coming, guys. This is all coming. Let's try it out. Let's start with just some matching first. Just some matching, and then we'll try some by hand. Okay, So in part A, which is this function here, first thing I want you to notice is that if I were to draw tangent lines to this function, they would all be negative sloped. They're all facing down. So that all the slopes for all the different tangent lines for this particular function would all be negative. Okay, so that translates to a graph where all the y values are negative because the slopes of the original function correspond to the y values on the graph of the derivative. So if I were to look at all these, I only see one, this one right here, where the slope, or sorry, excuse me, where the y values are all negative. They're all below the x-axis. Another thing to look for is that as x moves to the right on this curve, the slopes would be getting less steep. They'd be getting flatter. If I look here, the slope actually looks pretty steep originally right there, but as I go over more in this direction, the slope looks not very steep at all, rather flat. So what do we know about flat slopes? Those are small decimals, right? The rise over run would be small decimal. That would be something close to 0. So that's giving me some confirmation that this graph right here is correct because all of the y values are negative, which matches the fact that all the slopes of this function are negative, and they're getting closer to 0 as x moves to the right, which matches the fact that these slopes are getting flatter, less steep, as x moves to the right. So we can deduce that the derivative for the graph in A is this graph right here. We've just matched A with 3. Looking at letter B, if I were to draw tangent lines, lines that just touch the curve and don't cross through it at all these different points, they would all have positive slopes. And so when I'm trying to find the derivative for this graph, I would want to look for a derivative that has only positive y coordinates. Why? Because the slopes on the original function correspond to the y values on the derivative. Say it with me. The slopes on the original function correspond to the y values on the derivative. That is going to be our mantra for the next few days. So I'm thinking it's this one here because this graph is the only one that has only positive y values. Notice how the largest y value is right at 0. That matches what's happening with this graph because this graph looks like the tangent lines would all be fairly flat, like they're not very steep, except right in the middle. That's like probably where the steepest tangent line would be. If I were to kind of draw one right in there, it looks like it would be 1 actually, a slope of 1. So it looks like that's why this function has the highest y coordinate. Why? Because the slopes on the original function correspond to the y values on the graph of the derivative. So if the original function is steepest at 0, at x equals 0, then the derivative will have its maximum, have its highest y value at the x value of 0. So the derivative for the graph of B would be this graph you see in number 4. Let's try C. C, we have a quadratic equation facing down, parabola facing down. So on the left side of, actually let's start with the 0. Right at 2, you can see right here, if I were to draw a tangent line, it would be a horizontal tangent line, and we know that horizontal tangent lines have slopes of 0. So I'm going to be looking for a derivative graph that has a 0 right when x is 2. Why? Because the slopes of the tangent lines to the original graph correspond to the to the y coordinates of the derivative. So I'm thinking it's going to be this graph here, because this graph has a y value of 0 at x equals 2, which would correspond to a horizontal tangent line with a slope of 0 on the original function at x equals 2. So let's check. So it's positive to the left of 2, which kind of matches what's going on this graph. On this graph, if I were to draw tangent lines to the curve to the left of 2, they'd all be sloping positively. So it makes sense that I'd have positive y values to the left of 2, whereas to the right of 2, if I were to draw a tangent line on this side, it would be sloping negatively. So I would have negative y values on my derivative graph. Why? because the slopes of the tangent lines to the original function correspond to the y coordinates of the derivative. Negative slopes correspond to negative y values. So the derivative for the graph of c is the second graph here. Why don't you guys try D and E? Okay, so hopefully you guys noticed that the graph of D corresponds to the graph number 5. Well, a couple things you can point out. There's two turning points on the graph in D, two places where we would have a horizontal tangent line, and slopes of horizontal lines are 0. So that's two different zeros on the graph of the derivative. That would be, the first one would be between -1 and -2 like we see in this graph, and the second one would be between +1 and 2 like we see on this graph. Then to the left of the first 0, the slopes are negative and then turn positive, and I can see that's what's happening on my derivative. The y coordinates were negative to the left of this 0 slope and then turned positive to the right of that 0 slope. And then over here for the other 0 slope, the slopes on the left were positive, so that makes sense that the y values on this graph were positive up until this decimal value, this x value between 1 and 2, where the slope was 0, and where on the derivative the point was 0. And then after that it has negative slopes, which correspond to these negative y values on this graph. Okay, so then that leaves E with 1, because the slopes start off as negative, they go to 0, and then they turn positive. And so we have negative y values, a 0 at 0, and then positive y values. Okay, so that's kind of some practice with matching. Now let's try to do it by hand. So in example 2, we have this graph here, and we want you to try to sketch the derivative of it. So let's try that out on a fresh graph grid. So the first thing we notice is that right here at -3, there would be a horizontal tangent line, which would correspond to a y coordinate of 0 on the graph of our derivative, since the y coordinate on the derivative corresponds to the slope of this line, and we keep the same x value, right? So if the slope of the line tangent to the graph at the x value of -3 is horizontal, then on the graph of f prime, which is what this would be here, the y coordinate would be 0 at that same x value of -3. And then I see that again right here. At the x value of 1, my original function, right, the graph of f, has another horizontal tangent line, which would have a slope of 0. So then that corresponds to a y value of 0 on my derivative graph at x equals 1. Then, because these are all changing slopes, it's really difficult and not really possible to find the exact slopes of all the different tangent lines. So we look more at the sign of them rather than the actual value. So like, for example, I can see if I draw a tangent line slope over here on the left side of -3, they're negative, right? As the x values move toward -3, those tangent lines I just drew in had negative slopes. And they were getting less and less negative as I approached -3, which means that the y coordinates would do something like this. And I'm just kind of guesstimating here, right? I'm not expecting you to do much more than just kind of sketch in some negative y coordinates, right? These were negative slopes. So then I had just values that were below the x-axis, but heading toward 0, because the slopes are getting flatter, less steep as the graph moves toward the x value of -3. And then I can see that from -3 to 1 on the x-axis, if I were to draw in slopes, they would now be sloping upward, right? This would have right here, there'd be a positive slope right there. So it looks like all my slopes until 1 will all be positive, except that as you get closer to 1, kind of a similar thing happens where the slopes are getting flatter. So it's going to kind of go up and then down. It'll have positive y values, but we can see the slopes kind of got steeper right around the middle. Right around, I would say between 0 and 1 was probably where the steepest slope was. And it's kind of hard to tell the slope value, but I don't know, maybe we could say it has like a slope of 3-ish, right? It's going up 3 and over 1 approximately. So maybe we could have our graph go up to 3. So kind of maybe go like that and then back down to 0. Now again, I'm just asking you to kind of roughly sketch. So if you didn't use 3, that's okay. As long as you had it sort of go from like steeper, it was like a flatter positive, like right there. Those tangent lines at first, right after you pass -3 are kind of flat, but then they kind of get steeper. But then as you get close to 1 and you're drawing in those tangent lines, they kind of start to get flatter, meaning these slope values are getting closer to 0. So then these y coordinates on the derivative are getting closer to 0. So something like that. So I'm kind of making a shape now, right? And the shapes may vary a little bit at this stage in the game. So it has a 0 at -3. It was negative to the left of there. And then it kind of goes up and down. And then after it passes the 0 slope, the slopes look like they're going negative again. In fact, it looks like they're getting rather steep negatives. So it looks like it's kind of dropping down this way. So maybe like right there. I'm putting an open circle because on the graph of my derivative right here, we have what's called a sharp turn. We're going to learn about that in our next section. A sharp turn is where a slope on original function sharply changes. It was like a steep negative on the left-hand side of the x value of 3, and then it changes to be a steep positive on the right-hand side of -3 with no smooth transition in between. So that creates a jump on the graph of the derivative. Now I'm jumping up to 3 because if you look at this line, see when your function's a line, then it's really easy to find the slope. You just do rise over run. So I'm going to use this point, and I can see it's going up 3 and over 1. And it's going to continue to do that, right? Up 3 and over 1 forever because it's linear. So I know that my y coordinate on the graph of the derivative from the x value of 3 and on will be constantly 3 because the slope of the function from the x value of 3 on is also constantly 3. And the slopes of the original function match or correspond to the y coordinates of the derivative. So I don't exactly know how negative this slope gets right here, but it just goes negative for a while. And then right at the x value of 3, it just jumps from a steep negative slope to a positive slope of 3. And the derivative actually doesn't exist at a sharp turn. So that's why both of these are open circles. Okay, so that's example 2. And again, your values for y may vary, and that's okay as long as you kind of have the overall signs of the slopes. So, and the 0 slope. So I had a 0 slope at -3, a 0 slope at 1. I had negative slopes on the left, positive slopes in the middle, negative slopes on the right, and then a sharp turn to a positive slope. This one you had to know the exact value because it is linear. So for linear functions, we do expect you to get the exact slope. And that's mostly what we're looking for. So why don't you guys try this one? Pause your video, get a second grid, and see if you could generate the graph of its derivative. Okay, so let's see how you did. The graph is starting to unveil itself now, slowly. Wait for it. Wait for it. It's coming. So hopefully you guys have a graph that looks something like this, where first thing we would notice is that this function looks really flat at the x value of 0, meaning a tangent line right there would be horizontal, which would have a slope of 0. That slope of 0 would translate into a y value of 0 on the graph of the derivative. Then the slopes are all positive. Like this whole entire graph has only positive slopes. On the left side, if I drew a tangent line, it would be positive. On the right side, if I drew a tangent line, it would also be positive. And the slopes get like pretty flat when you're close to 0. So like in the middle, the slopes are a little bit flatter, which is why on my graph of a derivative, the y values are closer to 0 because those are coming from slopes that were almost 0. And then as you move toward the right, the slopes would get steeper. And if you move to the left, the slopes would get steeper. So on the graph of the derivative, on the right side, you have higher, more positive y values that are corresponding with those steeper slopes. Same thing's happening on the left. So again, you see, this was a cubic function here. Its derivative turned into a quadratic function. Anyway, that concludes our video for this section, and we'll do some practice in class, and I'll see you there. Bye.